All right, a major application of the fundamental theorem of calculus is that we can use it to find areas between curves. So what do we mean by that? So let's just take a look here at an example. Let's draw two functions. Let's say we have a top function in green. Well, first let's establish we're going to integrate. We're interested in the area trapped between these two curves over the interval from a to b. And our functions look something like this. We have one on top. Whoops, sorry, we want to do that in a green. We have one on top, and then I have one below it. Something like that. All right, so definitely there's going to be some area underneath both of these curves between the curve itself and the x-axis. And we could use the integral for each individual curve to find that area. So let's give these some names. Let's call the top one f of x, and let's call the bottom one g of x, or maybe I should call them t and b. No, just g of x. Don't overthink it, right? Okay, top one's f of x, bottom one's g of x. So we're after not the entire area, but the area between. Area between. And so what is this area? Well, the green one, for the green function, the top function, f of x, if we integrate it over the interval a to b, integral from a to b of my top function, f of x dx, I would get the green area, right? And if I want the area in between, we got to think, okay, so how does this red area come into play? Well, the area under this red function is the integral from a to b of g of x, the bottom function, dx. So if I take the entire green area and subtract away the red area, I definitely get the area between these two curves. So using properties of integrals here, since we could split it up over addition, we can kind of put it back together. F of x minus g of x in one integral, the difference of the two functions, gives us the area between the two functions. And so for this particular example, note that we have all kind of positive area. We talked about signed area, right? So f of x is bigger than or equal to g of x on our interval a comma b. So the top function is above the bottom function is what that really says. F of x is greater than g of x. It doesn't cross over, because if it crossed over, and we'll do an example of where it crosses over, you may have to change which one is the top and the bottom. So sometimes people find this helpful to think of this as the top minus the bottom. And that's not a bad trick. So in this case, both of our areas were positive areas with respect to signed areas that the integral would give us. So that might ask the question, what about negative area below the x-axis? Okay, well, let's draw a picture of that. Okay, so, all right, again, over the arbitrary interval a to b and two made-up functions, we'll have our top function be f of x, and that'll be from a to b, that'll be this green area here. We know how to do that integral. And now we're going to say that we have a function that has some negative area down here, g of x. And that'll give us this negative area, if you will, with respect to signed area. So it turns out that we can use the same integral. The area between f of x and g of x, just like above, is equal to the integral from a to b of f of x minus g of x. Let's take that apart and kind of see why this makes sense. Well, so we're going to split this up into two integrals. We'll have our green interval from a to b of f of x dx, and then we're going to subtract our red area from a to b of g of x dx. And so what do we get here? Well, we get a positive area for the green guy minus a negative area for the red guy, but that ends up with positive green area minus a negative means positive, we add the red area, and we get the, that doesn't much matter. We end up with the actual area. between our two curves. Okay, so I don't have this written on my notes, but let's just think about what would happen if we had two sets of negative area here. Let's just give ourselves a new page here. Page manipulation, insert one page, go ahead, add it in. Okay, so after this we have one blank page here. Okay, so what about if they're both below the x-axis? All right, so again, our interval from A to B, and this time f of x is here, f of x, and then g of x is something like this, whoops, in red, g of x. All right, can we do this same game? You got your green, and then you got your red. And it turns out it's going to work. So the area, and in this case, the area between would be this area trapped between our two curves. Between is going to be equal to, well, our top function would be the integral. So top would be the green one, f of x dx, and then subtract the bottom function, integral from a to b of g of x dx. And what are we going to get? Well, we're going to get a smaller negative area for the green, since it's a smaller area physically, minus a larger negative area in red. And so putting that all together, you end up with a smaller negative area in green being combined with, because negative times negative gives us plus the larger what's now a positive area, because the way algebra works, negative times negative gives us a positive. And so you're really taking the bigger area in the positive, correct sign, and taking away the smaller area, and you end up with the area between them. So it doesn't matter whether or not you've got functions above or below the axis. You can always subtract the top one from the bottom one, and you get the area trapped between the functions. So let's pause here, and then we'll work a bunch of examples of this.